And welcome back to week 5, ladies and gentlemen. We are looking at nuclear chemistry this week. So we're back inside the atom at the nucleus. So today you're going to be watching this lecture in Google Classroom, and then you will be answering the lecture questions in the Google Doc that'll be attached to this lesson in week 5 of distance learning within Google Classroom. So you can find the two attachments there along with the PowerPoint notes that'll be attached to the agenda for today. So let's get started with looking at the nucleus and changes in the nucleus. We've thus far written elements as just symbols, like AU for gold or a capital H for hydrogen. And this new way of writing isotopes, called isotope notation, is not just the symbol, but it's also going to include the atomic number and the atomic mass. So to give you a couple examples, we've got lead, which is called lead-209, and then uranium, which is called uranium-238, based on their atomic numbers. So the number at the bottom is the atomic number, which is the number of protons, also the same as the number of electrons. And then your number at the top, the 209 and the 238, are the mass numbers of the atoms. So we can use the mass number. The mass number is the combined totals of the protons and the neutrons together. So those have been combined or added together. So this bottom number being the number of protons or the atomic number added with the number of neutrons present in the nucleus of this particular isotope of lead-209 or uranium-238. So remember that the top number minus the bottom number, or our mass number, 209, minus atomic number of 82 is going to equal the number of neutrons. So if you want to find out how many neutrons there are within one of these nuclei, you can simply subtract the 82 from the 209, or the 92 in the case of uranium from 238. So what is an isotope? We said we're using isotope notation for nuclear chemistry. An isotope is an element, and these elements have multiple forms of the same element, because an element can have different numbers of neutrons and still be the same element. So we can change the mass without changing what the element is by adding neutrons. So here's one such example with hydrogen. If we look at hydrogen having a mass number of 1, right, that's based on 1 proton because there's 0 neutrons. If we add a neutron to the proton, right, so it's still got 1 proton as the atomic number would indicate on the bottom, but we've added a neutron to that now, and that makes it a mass number of 2. If we add 2 neutrons to the 1 proton, that takes us to a total of 3, which is now a mass number of 3. We can do the same for uranium. Uranium can be 235 or it can be 238. 235 has 143 neutrons. It's 235 minus 92. That gives you 143. Uranium-238, taking away the 92 protons, is going to have 146 neutrons. So we've added 3 more neutrons to the U-235 to make U-238. And that's going to give you 146 neutrons. So these nuclei can react because they are unstable. The reason they would be unstable is that they have either too many or too few neutrons. There's what's called a band of stability, or a region, kind of a range at which nuclei are stable. And if you add or subtract neutrons from that, it changes, obviously, that range. And so it shifts outside of that range of stability, thus making it unstable and prone to a nuclear decay reaction. So these isotopes do decay. They break down into smaller pieces that are more stable. That's the reason they break down, is to become more stable or less reactive in the nucleus. We call these isotopes radioactive isotopes because they do break down and undergo decay to become stable. So there's two ways that they can undergo this process of decay. There's alpha decay, which is represented by this Greek letter alpha. And in alpha decay, what's given off or broken off of that unstable nucleus is an alpha particle that's made up of four particles, two protons and two neutrons. So an alpha particle has a mass of 4. You can see the difference here from 238 down to 234. So there's a total of 4 particles in the mass that are being lost to that alpha particle, and then 2 particles from the atomic number, or the protons, that are lost, and that creates thorium. But we've got 4 over 2 for the mass and the atomic number of the alpha particle. The beta decay is denoted by the Greek letter beta. The elements are giving off what's called a beta particle during beta decay. So you can see that the beta particle has a negative, and calcium, in this case, calcium 47, undergoes beta decay to create selenium. Notice the mass is still the same, 47 and 47, but the atomic number changes from 20 to 21. So the atomic number is actually increasing because the atomic number of the beta particle is -1. Now, these different processes like alpha and beta decay depend on the element and how long it takes for that element to break apart. Some of these are a matter of seconds, some are a matter of days, like the iodine example here, iodine 131. Only takes 8 days to break down. Iodine 129 takes 15.7 million years. So definitely a lot more stable than the iodine 129. We call this time it takes to decay a half-life, which means half of any given sample is going to undergo radioactive decay. So this is a curve, decay curve, of the iodine 131 that takes 8 days. So we see the first plot going from 0 days to 8 days. 50% of this has undergone decay. Then to go from 50% down to 25 to get the other half to decay, it's going to go 16 days. So 16 days out, only 1/4 of the sample would still be radioactive. So what can we use nuclear chemistry for, or these radioisotopes for? Medicine is one way that these are used in a lot of imaging techniques. They allow for resolution of organs. They also allow for fighting cancer and killing off cancerous cells. The example over here to the right shows a thyroid scan after taking radioactive iodine. So you could see the thyroid due to the radioactive sample of iodine that's taken in. We can also make nuclear batteries. Nuclear batteries are used and important in spacecraft, satellites, pacemakers, right? So that they can continue to run for long periods of time without needing any intervention or maintenance. They've also been used for glow-in-the-dark watch hands at different times. So radioactive tritium, like this watch example here on the right. So that concludes our overview of nuclear chemistry and nuclear decay and some of its applications. So I'd like you now to attempt to answer to the best of your ability the lecture questions that go along with this lecture today, and then submit those through Google Classroom to me, and I'll look forward to reading your responses. And if you get stuck, reach out via email or Remind, and I will assist you with where you're stuck. We'll see you next time.